The broadcast is now starting. All attendees are in listen-only mode.
Good morning and good afternoon, and welcome to the June Pacific Northwest DEWS Drought and Climate Outlook webinar. My name is Britt Parker, and I'm with the National Integrated Drought Information System. This bi-monthly webinar series, hosted by NIDIS, the USDA Climate Hub, Northwest Climate Hub, and the Oregon Climate Change Research Institute, is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the regions. Webinars and recordings and other supporting materials will be posted on drought.gov later this week, and you should all receive an email once the recording is available. Please note that after today's webinar, you will have the opportunity to provide feedback that will help us improve this webinar series. So please take a moment and tell us what you think. Today's speaker includes climate recap and current conditions from Karen Bumbaco with the Office of the Washington State Climatologist at the University of Washington, seasonal conditions and climate outlook with Joel Cosola with NOAA's National Centers for Environmental Information, Western Region. And then we will have a presentation from Zach Hoylman with the Montana Climate Office at the University of Montana on some recent research entitled Drought Assessment Has Been Outpaced by Climate Change, Empirical Arguments for a Paradigm Shift. You'll notice we only have 3 speakers today. I think we had some interesting potential speakers, but we couldn't quite make the summer schedules work with the webinar schedule. So we'll be a little more relaxed today, and we'll allow questions to come in and be answered after each speaker, and then we'll also have some time at the end. So before we begin the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Please visit the website listed to get more information. And we'll also put these websites in the chat box. The Oregon Climate Change Research Institute is a network of dozens of researchers in Oregon's public universities that work closely with other public and private entities. OCRI is housed at the Oregon State University and advances understanding of regional climate impacts and adaptation and cultivates climate-informed communities. NOAA was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across the region. Each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of their regions. The Pacific Northwest DEWS was officially launched in February of 2016, and our strategic plan and information on current activities is available on drought.gov. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCOROS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique, nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, rain, hail, and snow, as well as condition reporting. Observations by COCOROS observers of precipitation events or the lack thereof are important to capture and improve our understanding of weather. To become a volunteer or to learn more, visit cocoros.org or contact your state coordinator. We'll place the names and their emails in the chat box shortly. Finally, I just want to highlight that NOAA's National Integrated Drought Information System, NIDIS, as well as the National Integrated Heat Health Information System, NIHIS, are hosting 2 webinars on July 21st in collaboration with federal, tribal, state, and local partners. The webinars will provide the latest information on current drought, heat, and fire conditions and forecast, as well as the serious impacts to diverse sectors of the economies and communities throughout the West and Southern Plains. Perspectives from those on the ground who are responding to these worsening drought and heat conditions will be shared. And again, we'll put the registration link in the chat box shortly. So with that, I want to go ahead and turn the presentation over to Karen, who is going to talk about the current conditions and the recent recap. So Karen.
Yep, I'm here and waiting for the invitation to share.
Coming to
Here we go. Does that look okay?
It does.
All right, great. Well, good morning, everyone. Pleased to talk with you today and give you the regional climate update for the Pacific Northwest. So our water year to date, the maps on the top here, we have temperature on the left-hand side going through June 22nd, precipitation on the right-hand side, and this is since October 1st, so the start of the water year. And we are now turning out to be a bit cooler than normal for the water year. Lots of blues on that map showing our temperatures below normal really throughout the region. And then if you look at October through May, where we have a complete month of data, the temperatures in Washington are definitely the coldest relative to normal, with about 1 degree Fahrenheit below the 1991 to 2020 normal, but closer to normal when you average throughout the state in Idaho, Oregon, and Montana. For precipitation, there's lots of spatial variability. You can see areas in western Washington, northwest Oregon, parts of northern Idaho, southeastern Washington, northeastern Oregon that have been above normal for precipitation. But when you average that for each state individually, we get near normal totals for Montana and Idaho, below normal precipitation for Oregon, and above normal for Washington. So that variability kind of cancels each other out in some of the states for the water year so far. Looking at the last 90 days, though, we get a much more consistent picture throughout the whole region. So this is going back to just the end of March through a few days ago in June. And region-wide, much below normal temperatures, really below normal. With looking at our rankings, if you just look at the complete months of April and May, it was the 3rd coldest in Washington, and this is using records that go all the way back to 1895, about 4.5 degrees Fahrenheit below normal average for those 2 months, so pretty substantial anomaly there. Tied for the 6th coldest in Idaho, tied for the 8th coldest in Oregon, and the 11th coldest in Montana. And that's averaged throughout the whole state of Montana, though I'm just showing western Montana here. So the anomalies are all at least 4 degrees below normal, which is, again, a substantial anomaly, as I'm sure you're well aware. For precipitation, wetter throughout the region for the last 90 days, and pretty consistent as well with that. Just looking at April and May, precipitation was the 4th wettest in Oregon and Washington, and the 16th wettest in Idaho. So definitely more of a wet signal west of the Cascades in both Washington and Oregon. Last 30 days, more of the same. So this is just taking the end of May through June. So on the previous slide, I talked about the rankings for April and May, but even continuing into June, we've seen, except for the last few days, much cooler and wetter than normal conditions. And then we have the rankings shown for each state there. So this is just for May. So 8th coldest, 16th coldest, 17th coldest, etc. And then among the top 13 wettest as well for just May. And I wanted to remind you that, where we were in late winter, we were in a much different place for the Pacific Northwest through about January 10th through the end of March. We were on the warm and dry side throughout much of the region, and then we've had a pattern shift since April. And so this is just looking at the atmospheric anomalies in the 500 geopotential heights, so showing what our circulation is like, comparing it to that dry period from January through March, and then to what we've seen recently. And so while this isn't exactly a La Nina pattern shown on the right-hand side since April, it's definitely much more favorable for cold and stormy weather in the Pacific Northwest. And so we can put some of this blame on La Nina for our late season cool and wet conditions. One thing to note is the sea surface temperature anomalies in the equatorial tropical Pacific Ocean, where El Nino and La Nina are typically tracked. Those anomalies were the coldest for April compared to all the other past Aprils since records began in 1950. So a really strong anomaly in spring, which was unusual, and I think definitely plays a role in why we've had this cold and wet pattern of late. So this is showing the US Drought Monitor changes that we've seen over the last 12 weeks. So pretty much just when we started seeing that pattern shift in early April, and we could see lots of improvements throughout the region. Those green colors are different classes of improvements just due to the cold and wet weather we've seen. This is the current drought monitor, though, still showing drought depiction through a lot of the Pacific Northwest. And this is mostly due to our longer term precipitation deficits at this point. So it's reflective more so of the dry spring and summer we saw last year in 2021, and then even further in parts of Oregon and Idaho. And I will also say that some of the reservoirs, while they're looking good in Washington, even with improvements that they've seen in this wet recent period, are still below normal throughout a lot of Oregon. But we have seen, like I said, improvements. So this is soil moisture on the left-hand side. This is a NASA depiction showing greens and blues, where it's now normal to above normal, which is another big shift from what we were seeing in late winter. And then the 28-day stream flow showing here, which is mostly above normal throughout the region as well. So our impacts, I guess to start with the good news, is that winter wheat, not winter, but just wheat in general, has been in good shape due to our wetter weather. And most of the impacts we're seeing are due to it being too wet. So some of the reports that came out of NASS have been saying, such as the US cherry production is down about 21% from 2021. And they were putting that blame on the cold weather we've seen in spring to reduce pollination and fruit set. And in mid-April, for example, so on the right-hand side, we actually saw some snow throughout some of those cherry growing regions of the Pacific Northwest, which is not great news for those crops there. And then of the most recent couple NASS reports, we're talking about disease issues in Northwest Oregon and fungicide treatment being needed. In Skagit County in Washington, areas of ponded water that impacted potatoes and vegetable seeds. In Chelan County in Washington, some hail and rain created some more loss to cherries, potential losses for apples and pears. And then in the most recent report last week, talking about in Washington and Whatcom County, some of the fields being too wet for tractors. That's all west of the Cascades, Whatcom County and Skagit, I should say. So not seeing many drought impacts at all, and getting to the point where we're seeing impacts from the wet conditions for our agriculture. So just to summarize, our water year temperatures to date are near normal to below normal, depending on where you are in the Pacific Northwest. Our water year precipitation is near normal to above normal for most locations, with there being more exceptions in Southern Oregon and Southern Idaho, exactly where we've been seeing even longer precipitation deficits. So that's unfortunate that this water year is aligning with that. Spring and early summer has been among the top 10 coldest and wettest on record throughout the region. Because of that, drought has improved region-wide, though our long-term multi-year precipitation deficits still do remain, with some below normal reservoirs as well, especially in Oregon. and most of the reported impacts have been in the too wet category. So that's all I had today, and we'll take questions if there's time.
Great. So I'll turn it over to Megan for questions while I go ahead and give Joe presenter control.
Sure, there's a couple of questions, Karen. One question is, has there been an accounting for increased humidity?
That I am not sure of. I did not look at that, so I'd have to get back to who asked that question on that one.
Okay, great. Perhaps the person who asked can email Karen. I think her email is in the chat there. A couple other questions coming in. So everything in Washington State is showing wet, cool, wet crops. Let's see. I guess the question is about finding things on drought.gov. Why rely on old precipitation deficits if everything recently has been in the cool, wet category for the drought?
Yeah, that's a good question. So are you talking about the Drought Monitor, I'm assuming? So even though there's been recent wet, there's still some lingering impacts. For example, in Washington, like groundwater levels are still much below normal, really throughout all of Eastern Washington. Due to our drought that we saw last year, there can be longer term impacts ecologically, for example, as well. And then also another one we've heard is sometimes, even though wheat is looking good this year, some agriculture maybe forgoed planting wheat because of the dry spell last year. And so there can be kind of compounded effects where it's not completely wiped out from one wet spring.
All right, thank you. Let's see, Britt, do we have time for another couple questions?
Yeah, I think you can ask another one.
So our question is, are Oregon reservoirs, are the Oregon reservoirs that are still low in the south, since most of the Willamette's reservoirs appear to be normal?
Yes. Sorry, I did not say that explicitly. Yeah, Northwestern Oregon has seen a lot of improvements on the Drought Monitor for reservoirs. So yeah, it's in the southern part of the state where we're seeing some of the longer term stuff. Okay.
And then are you able to comment on the fact that Lincoln, Grant, and Douglas counties in Oregon are said to be about 80% moderate drought, which doesn't seem to make sense in that area?
In Oregon?
In Oregon.
I'm not sure.
Oh, sorry, no, in Washington. Sorry.
Okay, I was going to say, I don't know where those counties are in Oregon. Yeah, so that would just still be, I mean, pretty much the same thing I said before about the longer term precipitation deficits there and the groundwater. There's also some areas where soil moisture, like further below, just not the surface, are also showing signs of drought.
Okay, and then a related question, where can one verify long-term groundwater deficits? Is there a resource?
Yeah, let me get a link. I can put that in the chat. It's from USGS, but I have to find it.
Okay, and then one final question. What is the danger to the bird, worm, and insect populations of using more fungicides and herbicides to control unfavorable growth caused by an increase in temperature?
Yeah, that one I'm not so much an expert on, so can't comment.
All right, thank you, Karen. Those are all the questions for now.
Great, thank you. And Joe, we'll turn it over to you.
Thanks for having me. Hopefully you all can see my screen. And just to chime in on that one question, a couple questions about kind of the long-term drought condition. So some of the indicators that the Drought Monitor draws on are actually from the last 60 months, so 5 years of kind of hydrologic condition, which can correspond to, as Karen mentioned, groundwater or deeper soil moisture conditions. And so, yeah, despite having kind of the pretty wet water year and a pretty wet couple months, in many places we're still catching up, and so you still see some areas that that look like they're in drought or are deemed to be in drought, even if they've had recent wet conditions. Well, I'm going to take a little bit of a longer view on where the climate has been, as well as to talk about where things we think are going. But before I do that, I did want to, just do a quick public service announcement. It's pretty hot in the Northwest today, and it was pretty warm yesterday. So just, and these are the forecasts for today on the left and tomorrow on the right. So please, if you have to be outside, take it easy, stay hydrated, check on your pets, check on your neighbors who may be elderly or may have some health problems. I've been doing a lot of work with NIDIS lately, and they've really kind of educated me in how dangerous heat can be, especially in places when it's early season and folks are not acclimatized to it, or it's less common. So yeah, as Seattle and Portland, especially those coastal folks who may be less used to seeing the 90s, as you guys see that today, please take it easy, and don't worry, tomorrow will be much more comfortable. So the cheat sheet, or kind of the takeaways from my talk. I'm going to take a look at the stream flow consequences of that cold, wet spring, and a lot of the rivers in the Northwest Basin. The water supply forecasts are kind of above average. Then we'll look at a variety of outlooks. The 8 to 14 day outlook is kind of a return to cool and wet. July shows equal chances for most of the region, but some cool temperatures along the coast. The summer outlook, we get kind of more of a shift to warm and dry for the Northwest interior, but the coastal areas stay kind of equal chances of warm or wet, warm or cold or wet or dry conditions. I'll talk a little bit about the ENSO forecast that just got updated today. And then we'll conclude looking at the Drought Monitor as well as the fire danger forecast. So the stream flow forecast, and this is for the entire water year. Most of the cards have been dealt on this, given the rain and snow that we've had, and we've shifted to, well shifted to kind of the melt season finally. But you can see a lot of the blues and greens here show either right around the 100% of normal, or the blues are actually higher than normal. So you see a lot of those colors in kind of the northern 2/3 of the Pacific Northwest. But across southern Oregon and southern Idaho, you see a lot of places that are below normal, and some of them very, very far below normal. I'd like to also point out that, some of the stations in the Oregon Cascades, kind of along the Willamette River, they're seeing some of the highest ones on record. Some of those 158% of normal, 177% of normal. Those are some of the leading events in the stream flow record for those locations. And you can see that a little more clearly. I'm switching to show the percentiles. So where you see the blacks, you're really talking about kind of record-setting volumes of stream flow over the course of the water year. And similarly, a bad situation, or I should say the mirror image, are some of the things in kind of southern Idaho and southern Oregon, where you have things that are in kind of percentile values below 10. So really some really very low flow conditions for the course of the whole year. One thing I wanted to kind of revisit, this is actually the forecast from late April, I think one of Henry's slides, for the Snake River, Lower Granite Dam, so that's kind of near Walla Walla, I believe. But you can see the green dots are what the 30-year average for stream flow month by month is, and then the forecast was that we'd get kind of peak flow a little below average in May, and then things kind of falling off, close to what the normal picture might be. Then we had this incredibly wet April, incredibly wet May, and here's the kind of updated situation. So what we had was actually really high flows in May, and actually that was not far off, to be honest, what the forecast was, going back to the forecast. But that was not the peak flow. The peak flow is actually occurring right now. This blue bar is the observed flow already through June, and the yellow dot is where the forecast is. So we're going to have the peak flow, or at least at this part of, if we're dealing with thinking of naturalized flows, at least this part of the Snake and kind of the Columbia system, in June. And so we'd have that peak flow later than we would have normally expected. And then things kind of easing back into the later summer, kind of closer to normal conditions. But I think it's interesting what a huge impact that wet, cold spring has had on the stream flow behavior in the kind of northern, let's say 2/3 of the Northwest. My only impact slide will be on this note of too wet. And these are just two pictures kind of from the different parts of the Columbia. On the left is at John Day Dam, where the Army Corps actually had to hold back water for flood control in, I guess it was the second week of June, with the rain event that came through the Northwest. There would have been, I think, really awful flooding, or could have been pretty awful flooding in the lower reaches of the Columbia, and they were able to hold water back to help mitigate some of that. And then farther out west, around Walla Walla, they actually had a decent amount of flooding. Kind of the Hermiston area in Oregon. It was kind of the Pendleton forecast office, or the folks that kind of tipped me off to some of this. So it's kind of northeastern Oregon and southwestern, I'm sorry, yeah, and southeastern Washington. And so the picture on the right is from a flooded field. And some of the articles that I looked at, it was, the suggestion was not just, you know, did the heavy kind of consistent rains bring some of this, but that river channels may have been altered from heavy flooding in 2020. And so their kind of risk landscape is different. And a lot of the agricultural areas were the places that kind of buffered, you know, and absorbed floodwaters, that now floodwaters are kind of hitting roads and subdivisions and things like that. And so I think this idea of the landscape itself being non-stationary, in addition to the climate, is important when we think about future risk and future adaptation. Okay, getting to our outlooks. So this is the 8 to 14 day outlooks. You can see kind of that return to chilliness for most of the Northwest, and I think folks in California will actually welcome it, while a large part of the rest of the country is looking for above average temperatures. Precipitation wise, still kind of elevated chances for wet conditions in that already wet area of the Northwest, as well as you can see some of the kind of monsoonal, the active monsoonal activity in the Southwest, with kind of a bullseye for dry conditions in kind of the Great Basin area. For July, the better chances for below temperature area shrinks back to the coast, with most of the Northwest having kind of equal chances for above or below average temperatures, and really not much on the precipitation anomaly side, although it's kind of a dry time of year, so you know, not much action is to be expected. Looking at the summer as a whole, the above average temperatures, or elevated chances for above average temperatures for most of the West, the coast may be spared here. And then the seasonal precipitation outlook shows for elevated chances of dry conditions along a lot of the interior of the Northwest. And the drought outlook, on the left is June outlook, although June's kind of in our rear view mirror, but I think it echoes the story that Karen showed. You know, we've had a lot of rainfall across Washington state and the northern part of Idaho, as well as Oregon. And so you've had a lot of drought improvement. However, there's drought persistence across southern parts of Oregon and southern parts of Idaho. And that is anticipated to continue throughout the summertime. The fire potential maps kind of reflect in a lot of ways some of the where we've had drought conditions. The fire potential is above normal, and so you see that through southern Oregon, as well as up into central Washington, those places that are kind of clinging to the long-term drought. You see parts of Idaho kind of getting colored red into August. I do want to point out, though, with these, places that are colored white doesn't mean that there's no fire. It's just relative to what the normal fire activity would be. So there is certainly normal fire activity in parts of Idaho and and Montana in kind of a normal summer. I do think some of our cool and wet spring conditions are probably delaying the start of fire season, which is probably a good thing. Now I want to talk about ENSO stuff for the next and last couple slides. So this chart of a bunch of numbers, this is the Ocean Nino Index. So it's a measure of sea surface temperature in the tropical Pacific, and it's binned into 3-month averages, so kind of a slow evolution of temperature in the tropical Pacific. And it's just showing in the blues where we get kind of cooler temperatures, and that corresponds to a La Nina event, and the reds are El Nino events. And so you can kind of see at the bottom here, the emergence of the event for 2020/2021, then last year's event. And I think what's striking is not just that we had this double dip, but as Karen mentioned, really, really cold temperatures in kind of the springtime period. And normally during kind of El Nino cycles, you have a bit of a reset from the spring into the summertime, that things kind of come back to the mean, and then you may get an El Nino, you may get an La Nina, you may get neutral conditions, but you get this kind of reset, and we haven't really seen that much of that in the spring. Now that said, in the last couple weeks, there's been a little bit of a warm up, and you can see it subtly on these two graphs. On the left is that sea surface temperature from that same tropical Pacific region where we look at the ONI, and you can see that although things were really cold in the tropical Pacific in May, things have warmed up slightly, and you can see that the surface pattern of that evolved to the maps at the right. Oh, so subtle, kind of backing off of those really cold anomalies that you saw at the beginning of June, that they kind of shrunken and been reduced ever so slightly. How does this impact the forecast going forward? Well, you can see here, these are the ENSO probabilities, with the blue being corresponding to La Nina, the gray for neutral conditions, and the red for El Nino. So you can see that El Nino is barely even showing up on this graph, so almost no chance for that in for the rest of the calendar year and into early 2023. La Nina is still kind of leading the charge, although in kind of late summer, early fall, the neutral phase is very competitive, but the anticipated, or the kind of leading dog of the forecast is for La Nina conditions to continue through the fall and early winter. I think what will be interesting is, if obviously La Nina sets up for early fall, then it has much better chances of sticking around throughout the winter. But if it doesn't, if this forecast, if the gray somehow gets a little bit more competitive, I think it will be interesting to see if that alters our kind of anticipation of a triple dip of a 3 years in a row of La Nina conditions. Now, one thing, the kind of grain of salt I want to add to the La Nina or ENSO forecasts in general is that we're getting a lot of requests about, well, what does that mean for another La Nina year? And I tend to use caution that the ENSO condition is not really deterministic for our rainfall or for our temperatures in most of the continental United States. It shifts the odds for sure. It's definitely important, but it's not the only thing. And so these plots are for statewide kind of cold season, October to March precipitation for Washington, Idaho. Unfortunately, they didn't have one of these made up already for Oregon. And the blue dots show kind of the La Nina years, the red dots the El Nino years, and the green dots are the neutral years. And you see a pretty big spread in what that kind of fall and winter precipitation is. And if you look at the statistics, the amount of variance explained just by the El Nino index is not that big. And for the state of Washington, it's only, the R-squared is only 0.03. That's 3%. That means 97% of the variance in precipitation is explained by something else. In Idaho, it's a little higher. It's more like 11%, but still, you have a large chunk of the variability being determined or being explained by other factors. So And so certainly important. I don't want to leave you with the impression it's not important, but it's not the only thing. So we'll keep our eye on kind of the ENSO status. I think we can probably skip El Nino for 2022 and 2023, but we'll see how kind of the La Nina and the La Nada, as I've heard it called, duke it out. And that's all for me. I'd love to take questions if we still have a couple minutes.
Yes, there are several questions coming in. First question came in at the end as we were switching over to Joe's talk, but I think both Karen and Joe might be able to speak to this. So in the previous webinar, the NOAA speaker said that many areas impacted the most by drought would need 150 to 200% or more of normal precipitation over the next 2 months to lessen drought conditions. So the question is this rate of precipitation still the amount needed for the areas most impacted by drought?
Well, I think given that the average precipitation for July and August are so little, the numbers that you would need would be astronomical for, let's say, Southern Oregon or Idaho. I think that the reality is they're not going to recover from drought this water year. It's going to have to be more of a next water year, that the chances of heavy rainfall, let alone the amount to offset what the dryness that they've experienced the last several years, that type of rainfall is not coming this water year. I think it's safe to say, unfortunately.
All right, thank you. Next question is, what is the % increase in warm, humid days in Southern Oregon?
I don't know that off the top of my head. We can probably find a way that we can look that up as far as that, what has the trends been in temperature and humidity? And Karen, I don't know if you guys have any, like in your trends tool, if that's something that would be tracked easily or if that was just for Washington State.
Yeah, we have the trends tools for the whole Pacific Northwest, but we don't have any humidity. We have temperatures for sure.
Yeah.
Okay. Here's a comment. It looks like some of the maps you show coincide with the jet stream map. Is there a connection with the jet stream in the maps that you've shown?
Oh, absolutely. Yeah. So, Karen's two bullseyes, I think, were really, really great from showing the 500 millibar anomalies, right? There's a big ridge kind of January to March. And so things were probably kind of dry and a little bit warmer than average. And then the huge trough that kind of predominated through the April and May, and so that really delivered that stream flow picture, that I showed. That also was probably set up the antecedent moisture that helped with the flooding that occurred in June. So absolutely, that was kind of a big deal. As far as for the summertime conditions, we generally see the anomalies in the Northwest be not as large. The jet stream's not as big a player. That said, the upper air or the jet stream picture that goes with that, some of those outlooks, especially the 8 to 14 day outlook, is actually that continuation of a trough, just kind of off the coast of the Northwest.
Okay, a few more questions. Is Idaho Precipitation Twice that of Washington, and does that come from Snowfall or what?
I don't think it's twice that. Let's see.
Or were the slides?
Yeah, going back to this slide. Yeah, good observation. Yeah, that's a good question. I think it may just be kind of averaged over the big area. So a bunch of Washington State is probably really, really dry east of the Cascades. And you're right. I think some of the mountains in Idaho must be helping them look more wet in terms of intercepting a lot of precipitation. I wouldn't have guessed that. That's surprising.
Okay, we got a couple of questions. If you can provide the link to where the maps that show all of the stream gauges and the percentage of normal that you had in your
let's
slide.
See on there. There it is. Yeah, the Northwest River Forecast Center.
Okay, and that's the same one for the peak flows and forecasted flows. Is that right?
Yeah. So did I not let's see. I can add that. I can go dig that up and add this link. Yeah, because I actually copied this one from the last webinar. But yeah, let me drop that into the chat.
Okay, great. I think we have time for one more question. We'll come back to the rest afterwards. There was, okay, the fire potential outlook appears to skip Alaska. Do you feel Alaskans' wildland fire situation is accurately presented? The fire started just this last week due to lightning in Anderson, Alaska.
Yeah, I know the fires, there's some bad fires up there right now. Yeah, I didn't include Alaska in these, but I know they are included in the NIFC forecast. So that link should let you take a look at the Alaska situation. I know their forecast discussion is actually pretty lengthy for Alaska. Yeah, and so whether or not it's like does a good job, the NIFC forecast for Alaska, I don't know enough about a fire period / fire in Alaska to say, but yeah, I'll leave it at that.
Okay, thank you. We'll try to get a few more questions at the very end if we have time. All right,
Great.
thanks.
Great, so we'll turn it over to Zach for our final presentation today.
All right. Hi, everyone. Thank you. My name is Zach Hoylman, and I'm a research scientist at the Montana Climate Office and a research assistant professor at the University of Montana. And I'm excited to present some of our most recent work entitled Drought Assessment Has Been Outpaced by Climate Change, Empirical Arguments for a Paradigm Shift. Before I begin, I would like to thank NIDIS for inviting me to give this talk and for providing some of the funding to conduct this research. All right, I just wanted to start this talk by thinking about drought in the United States generally and reflect on its impacts on communities and people of this nation. This will not be groundbreaking to the group that here today, but drought has significant effects on agricultural and ranching communities across the country. And in fact, it's been estimated that major drought events since 1980 have cost an average of $9.3 billion in damages per event. National risk mitigation efforts are in place to help communities impacted by drought. Some of these efforts include livestock and agricultural insurance programs that help producers persist through extreme events. And financial assistance associated with these disaster relief programs are essential to sustain our national agro-system through periods of abnormal dryness. Drought monitoring is used to trigger these economic relief programs and is supported by a large community of scientists and water resource managers across local, state, and federal entities. Nationally, this effort is led by scientists at the U.S. Drought Monitor, which you've heard quite a bit about today. So how do we monitor drought? Well, one popular method is using a variety of drought metrics, not unlike what we've been hearing about today. Drought metrics use historical conditions to contextualize how current conditions compare to a reference period. Drought is, by definition, an abnormality in dryness. And in order to determine anomalies, drought scientists use a reference period to define the expected distribution of outcomes, given some historical observed variability. In general, conventional methods in drought science prefer longer periods of record to define the reference period. And this convention is generally supported by suggesting longer periods of record incorporate a wider range of extreme events and therefore describe the true distribution better, especially at the tails, which is where drought occurs. However, the question arises, what if this distribution is changing in time? In other words, what if the underlying process is non-stationary? For example, if your reference conditions are fixed and aridity becomes the new normal, is that location in drought or experiencing average conditions? And this is the really important question. And this consideration highlights a few major questions in drought monitoring and leads me to the major questions of this particular research. Firstly, how much data is needed to accurately compute drought metrics? This question tests conventional methods in drought monitoring to understand the statistical requirements for parameterizing drought models. And two, do long or longer climatology lengths produce bias in our contemporary drought assessment? So to better understand how non-stationarity may impact drought assessment, I would like to describe our conceptual model. Let's consider a theoretical precipitation distribution that's changing over time. This figure shows the accumulated precipitation over some arbitrary time scale, say 1 month, 2 months, 3 months, on the horizontal axis. And on the vertical axis, we show the associated probability density function. It's the probability of observing some amount of precipitation. The different colored lines represent the different time periods, starting with a 30-year time period at the beginning of the 20th century, to the current 30-year distribution shown in red. In this location, precipitation dynamics are getting drier and more variable over time. Here we can see that the driest conditions early in the century, shown on the left side of the blue distribution, are closer to the average conditions for mid-century, shown in the green, and are actually relatively wet when compared to the current 30-year distribution. So this idea has serious implications for computing drought metrics. For example, if we use conventional methods for computing the expected distribution, we would prefer to use the longest reference period possible. This is represented using the black line on the right panel. In this case, the driest expected conditions for the temporally integrated distribution, or the full period of record, are actually only slightly dry when compared to the conditions expected based on the most recent 30 years. If we were to observe an event such as this, the severity of the event would be considered more severe than is relevant given contemporary conditions if we used the full period of record. So do we see evidence for this temporal shift? Here's data from a Global Historical Climate Network, or GHCN, site in South Carolina. And what I'm showing here are the parameters used to describe precipitation dynamics. On the horizontal axis is time, and on the vertical axis is the parameter value. I computed these values using a 30-year moving window that shifts every year. What you can see is that there's a nonlinear and directional change in these parameters through time. And this is associated with changes in the precipitation central tendency, or average precipitation, and the variance over time. And in general, this site has been getting drier and more variable over time, which is similar to our conceptual model. To better visualize this, we can plot the associated probability density functions, or those estimates of how likely any specific event is over time, color scaled by time. The black and white dashed line shows the temporally integrated distribution using the entire period of record. This analysis shows that precipitation dynamics at this site are non-stationary and changing. And this idea is not particularly new. We know that precipitation dynamics are changing through time and has influences on water resource management decisions. But there's still a need to intentionally incorporate this concept into modern drought monitoring. Okay, so if we assume that climate is non-stationary, it is important to understand how much data is really required to accurately parameterize drought models. This brings us back to question 1. To address this question, we can use Monte Carlo simulation methods to estimate drometric error. This is a way of randomly sampling data to try to assess error. To do so, we'll begin with a known stationary distribution. And using this known distribution, we can quantify the relative change in error associated with differing climatology lengths to define the reference period. Here, we're going to be using the absolute error in the associated standardized precipitation index, or SPI value. But it's really important to understand that while we're focusing on SPI in this particular analysis, the concepts I'm presenting here today are relevant to any metric that uses historical conditions to describe anomalies. For example, temperature percentiles, or SPEI. Then we will modify this method to use observed estimates of climate from GHCN sites to estimate and emulate a non-stationary condition. So let's start with precipitation distribution that's well described using a rate parameter of 0.03 and a shape parameter of 2.5. To obtain these results, we used Monte Carlo and generated random data from the known distribution and randomly sampled that data over differing lengths. We then estimated the parameter values using based on the random sample using what's called L moments. And the horizontal axis shows the number of observations in the climatology, and the vertical axis shows the estimated rate and shape parameter values. The black line represents the median estimate over 1,000 iterations, and the gray ribbon represents the interquartile range of those estimates. As you can see, the range of estimates shown as the gray ribbon width is very large with a very limited sample size, say 3 observations. This means that it's hard to parameterize a distribution using so few samples. This uncertainty declines significantly when 15 observations are included. And from there, there's a modest reduction in uncertainty from 15 to 30 observations, beyond 30 observations, there's relatively small reductions in uncertainty. And if we extend this analysis to estimate the associated cumulative distribution function, or SPI absolute error, we see a similar decline in uncertainty and error. SPI error declined sharply from 2 to 15 observations, and then error decline then slows substantially to achieve an average error in SPI of 0.16 when 30 samples are included. Again, only minor reductions in error are then associated with sample sizes extending from 60 to 90 observations. In summary, error is relatively low with sample sizes as small as 30 observations, beyond which only minor error improvements are made. So what this means is that we can use relatively short periods of record to accurately describe precipitation dynamics. But is this error curve parameter specific? For example, maybe I just chose a parameter that was easy to calibrate. Well, here we extended the analysis to include random samples from an observed parameter space of almost 5 million calculations. And as you can see, a similar error curve is generally observed across all distributions, confirming that this error analysis is generally applicable to common SPI calculations performed in the US. This analysis brings us to an important question. What is the relevant reference period for drought? It is important to remember that drought is, by definition, a relative phenomenon, both in space and, importantly, in time. When we consider that real-time management decisions are made based on operational drought monitoring, it is clear that this monitoring is designed to assess and mitigate current-day risks. Without a dynamic reference frame that's changing through time, some places may transition to a state that is considered to be in drought on average with respect to the last century. Alternatively, if a shifting reference frame is adopted, anomalies will reflect current climatic variability and current day expected distributions. Besides, shifting reference frames are quite common in climate science. 30-year climate normals have been adopted to at least impartially account for non-stationarity and have been formally used since the 1930s. This is critical to describe realistic expectations of climate variability. And as an example of this practice, here are temperature normals computed for the continental United States compared to the last century. As you can see, temperature has been warming gradually across the country for the last century. In this case, if we did not adapt a reference frame that was shifting through time, one would conclude that most, if not all, annual conditions are anomalously warm during the most recent period. While this is true from the perspective of the century scale reference frame, it is not necessarily accurate from the perspective of the last 30 years. This practice of updating normals is used specifically to better approximate what conditions are likely to occur today. So why shouldn't drought monitoring follow this convention? So if a 30-year moving window convention is applied with the understanding that 30 years of data meets our statistical requirements, we can now begin to estimate how error changes across different sample sizes in a non-stationary environment or in a place where climate is changing. Here we are using a similar Monte Carlo style simulation, although instead of using a single distribution to generate data, we are using many distributions observed empirically from our GHGN site. In this case, we are estimating error for the most current year, 2020, by estimating the distribution using progressively outdated information as the climatology length increases. Here we can see that error initially declines similar to a non-stationary example, but then substantially increases after roughly 30 years. This increase in error is associated with the estimated distribution becoming increasingly outdated as older observations are included. In other words, the conditions from the early 1900s are not good representation of today's climate, so error increases. In summary, error can actually increase with greater climatology lengths if contemporary climate is significantly different than current climate. If we emulate this analysis across many sites and drought timescales, we can see that the error trajectory for any given location is site and time scale specific. And importantly, error does not necessarily decline with more observations. Given this analysis, a fundamental concept is highlighted. Drought monitoring must balance two distinct needs. Firstly, there are fundamental statistical necessities where a certain amount of data is needed to calibrate any distribution or model, stationary or otherwise. However, in a non-stationary environment, using too long of a reference frame may skew your expected distribution outside of realistic outcomes and increase error and potentially bias our assessment in drought severity. Which brings us to our second of our major questions. How long do long climatology lengths bias our drought assessment? To investigate this question, we're going to compute drought metrics for two different reference periods. The longest period of record versus the most recent contemporary 30-year climatology. This will allow us to empirically estimate the bias associated with using a long period of record. This analysis was conducted using around 2,000 GHCN sites across the United States with more than 70 years of complete precipitation rainfall record. We compute SPI for every day for each site between June 1st, August to August 31st, between 1991 and 2020. And again, this incorporates about 5 million calculations. And so here are the results using a 30-day timescale for the SPI calculation. In this map, we are looking at the daily average summertime bias in SPI from 1991 to 2020 during severe drought conditions. As you can see, a large portion of the map is red, which shows that the period of record SPI, or the conventional methods for calculating SPI, are biased dry when compared to the contemporary 30-year distribution. In other words, the severity of drought conditions are exaggerated when using the longest period of record. And in general, there's large portions of the West, Southwest, and Southeast that are affected by this dry bias. Perhaps most interesting for this group, alternatively, locations with blue colors represent locations where the period of record is biased wet, or drought severity using the longest period of record and precipitation data will be underestimated. These patterns are generally consistent across 60 and 90-day timescales, and these maps demonstrate the spatial patterns of this drought bias due to climate non-stationarity and highlight the need to reconcile this important consideration. We argue that leveraging a 30-year reference frame into drought monitoring balances statistical necessities with the need to accurately describe current day risk profiles and drought assessment. And with that, very quickly, I will just say that the implications of this research are primarily focused on aligning drought monitoring with contemporary drought risk. If drought intensity is assessed using stationary assumptions, drought severity will be exaggerated in locations that are experiencing aridifications. Alternatively, drought conditions will be underestimated in locations that are trending wetter, such as the Pacific Northwest. And by adjusting drought methods to be based on a moving window, drought assessment will better reflect current day drought risk to affected communities, be more standardized across data sets with differing periods of record, and account for climate change into the future. But ultimately, further dialogue is needed. And with that, I'd like to say thank you. And if you're more interested in diving into this research, you can find the associated publication in Nature Communications.
All right, I think we have time for one, maybe two questions, and any questions we don't get to today for Zach, we can follow up after the webinar, and we'll put all the speakers' emails in the chat so you can follow up with your questions directly if we don't get to them today. So question, have you calculated how the observation length impacts the error in only the low end of the probability distribution reflecting drought? And would you expect this to behave similarly?
That's a great question, and yes, I have. Here's a similar analysis that uses specifically the error in probability for a 1% drought event, or like a extreme D4 event. And what you can see is that the error trajectory is about the same in that bottom right-hand corner. The error is slightly higher than when you consider all SPI errors. But the trajectory of that error is the exact same as the previous analysis. So I believe that the conclusions still hold using this kind of rule of thumb.
Okay, last question. An argument for using a longer reference period, even though every current year might end up looking anomalous, is the lots of organisms, infrastructure set up for the range of conditions that used to be expected. Is there value in using both kinds of metrics?
Yeah, I think that there definitely is. And this is something that we're diving into. And it's this idea of what kind of drought are we really trying to describe? And different reference periods are going to be responsive to different kind of tempos of adaptation of different systems. Ecological systems, natural systems like forests are of course going to be responding on much longer timescales, I would argue, than something like an agricultural system. But because the drought monitor is used in many ways, and drought assessment in general in our country is used as a mitigation tool for producers in conjunction with these other types of organisms and processes and systems, we argue that in this case, we think that shorter reference frames are more reflective of kind of the adaptive capacity of agricultural systems in the United States. But I do believe that there is huge benefit in using both reference frames, and even out to really, really long reference frames like the mega droughts that we're talking about in the Southwest at the 1,000-year time scale are still relevant and interesting to and important for different processes, but perhaps aren't quite as useful as a shorter reference frame for risk mitigation, especially from an economic sense.
All right, thank you, Zach. That's all for today. So Britt, I'll let you close out.
Great, thank you so much. And as Megan said, we'll try to follow up if we didn't get to your questions. I have put the speaker emails in the chat box, as well as a reminder to join us on August 22nd for our next webinar. So thank you very much and have a great rest of your day and week.